Okay, let me introduce Professor Shen. So Professor Shen, Shun-Qing Shen is a professor of physics in Department of Physics, the University of Hong Kong. He got his BS, MS, and PhD in theoretical physics from Fudan University. And he is an expert in the field of condensed matter theory. Condensed matter theory, especially quantum transport, topological insulators, and spintronics of semiconductors, and quantum magnetism and optical physics in transition metal oxide, and novel quantum state of condensed matters. He proposed the topological Anderson insulator and developed the theory of weak equalization and with anti-localization in topological materials. He has published a single-authored topological insulators, 2012, first edition, and second edition is 2017. He's a real expert in topological material systems. Today, he's going to tell us about helical symmetry breaking and quantum anomaly. Please go ahead, Professor Shen.
Oh, thank you, Jihong. Thank you for your nice introductions, and also thank the organizer to invite me here to share my recent work on the quantum anomalies. So this talk is based on recent publications just published at the end of the last year. Have some new idea or new understanding about the quantum anomalies. So quantum anomalies is a purely quantum mechanical effect. It's actually this is extraordinary rich topics in the quantum field theories and these are high energy physics, actually not in the condensed matters. So this topic is attract our attentions just several years ago when the discoveries of the so-called topological materials. So people began to discuss these so-called quantum anomalies in condensed matters. So I teach the two courses. One is quantum mechanics, another is classical mechanics in the University of Hong Kong. So in the classical mechanics, we know that if we start from the Lagrangians of systems, if the Lagrangians is the coordinators is cyclic in the Lagrangians, that means so we can from the owner Lagrangian equations we can find that the so corresponding the momentums is conserved. So this is a famous Noether's the theorems. Since we call this is a theorem, so it should be exactly exact, right? So if quantities is conserved units, it should be satisfied some of the continuity equations. For example, if we know the charge is conserved, right? Charge is conserved. So the charge densities and current densities should be satisfied. These are so-called continuity equations. But in the quantum mechanics, start from the Schrödinger equations, we know that the probability should be conserved, right? We can also find another continuity equations for the probability densities and the probability that the current or flux densities. So that means that the conservations and these continuity equations are always connected. So when we talk about the quantum anomalies, we would like to start from the Dirac equations. So in the Dirac equations, we can discuss the so-called the chiralities and the helicities. So this equation, the hills, since we are in the condensed matter, we do not write these velocities as the speed of the light. Usually we would like to use it as the effective velocities. So we can apply these equations to the condensed matter system. So V is just the speed, effective the speed. So in these equations, we know the Hamiltonians can be expressed in terms of so-called the Dirac matrix Dirac matrix in 3 dimensions of the 4x4 the matrix. So Dirac find that this alpha and the beta is actually the 4 matrix can be expressed in terms of the so-called the Pauli matrix. So the 4x4 Dirac matrix can be reduced in terms of the 2 sets of the Pauli matrix. One we call this a sigma matrix, and another one is a tau matrix, just different notations, one for the spin, another actually for the so-called the bands. So from this equations, so here, since we use the express this Dirac matrix in terms of the 2 sets of the Pauli matrix. So these Hamiltonians you see can be expressed in very compact form. One is a p dot sigma cross the tau, and another terms is a sigma 0, means that is the identity matrix. So this tau is another Pauli matrix. So in this way, we find if we introduce an operator related to the p dot sigma, then this is we call this so-called helical helicities operators. We find this operator commute with the Hamiltonians. So this operator actually has the physical meanings. Units we define this so-called helicities is a projector of the particle spin at the directions of the momentums. So this is a physical observables. So from the Dirac equations, we find these are helicities, the symmetries. So another the symmetries is the so-called the chiral symmetries in the Dirac equations. The chiral symmetries actually is introduced a very special way. That you can, I don't want to derive this matrix here, but it can be expressed also in terms of sigma 0 times sigma tau 1. So this is also a 4x4 matrix. So if you calculate the commutator between the gamma 5 and the Hamiltonians, you find these terms actually is not equal to 0 if the particle has a mass. So this V set is a mass. But if the mass approach to 0, you'll find, oh, this gamma 5 operator also commute with the Hamiltonian. So in this way, so you will find for massive Dirac fermions, if the mass equal to 0, exactly equals to 0, we find the 2 symmetries. One is this helicities, another one is chiralities. Both of them commute with the Hamiltonians. So we say that this case, the system has a very high symmetries. But for massive Dirac fermions, the mass is not equal to 0. You'll find helical symmetries is still conserved. However, this chirality symmetries or chiral symmetries is broken by the mass terms. So this is they're different. But usually people like to say the helical helicity is sometimes equivalent to the chiralities. So that means in the massless case, if the mass equal to 0, we find these are 2, both of them commute with the Hamiltonians. That means they can be diagonalized simultaneously. So in this way, we can find the eigenvalues for their helicities and their chiralities, right? So this is a very good exercise in the quantum mechanics. So this is a p dot sigmas related to the helicities can be find the eigenstates and eigenvalues. P is the eigenvalue, H is equal to positive and negative 1, means the helicity positive and negative one means the different the helicities. Another eigenvectors is for the tau one. Tau one is a 2x2, the Pauli matrix. You can also easy to find the two eigenstates, right? One eigenvalue also equal to positive one and the negative ones. So you combine these two together, then we can diagonalize the 4x4 the Dirac matrix, the Dirac equations. So now the helicities, this is the eigenstate for both either the helicities or the chiralities. So the Hamiltonian is also diagonalized. This we have 4 the eigenvalues, but the 2 are doubly degenerated. So according to the signs of the energies, the energy can be positive and negative. The V is velocity, P is momentums. So you find if the H equal to tau, that means equal to positive one or negative ones. So this has positive energies. So if for the negative energy, so this H should be different by a sign from the tau. So this the 2 has a very close relations. So in this case, so now this has a so-called equivalence to the between the helicities and the chiralities. So for the positive energies, these 2 are equal. But for the negative energies, these 2 differ by sign the -1 by -1. So this is so-called equivalence between the helicities and the chiralities. Okay. So now there is a problem. Since we say these helicities and the chirality conserved in these Hamiltonians, right? So they should be satisfied some kind of the continuity equations if you can introduce the so-called helicity densities or chirality densities or helicity current or identity chirality current. So for the chiralities, so these are the current density has a very special name. They call it the actual vectors, the current. So in the absence of the electromagnetic field, so we know that this should be conserved. So if the gamma 5 is conserved, you should be satisfied. These are continuity equations. So even you introduce the so-called electromagnetic field in this system, you see the Hamiltonians is still satisfied. These are commutation relations. So that means in presence of the electromagnetic field, the chiral symmetry is still conserved. It's still conserved. So in this way, we expect these are so-called actual vector current and its densities should be satisfied these equations because the quantity is conserved, right? But however, in above the 1969, these 3 guys they found that these equations is not conserved, but it is satisfied. This is E is electric field and B is a magnetic field. So at the beginnings, this is very shock to the community of physics because since the symmetry is conserved, but you got equations which break the symmetries. So the people give a special name for this phenomena. They call this is so-called chiral anomalies. So at the very beginnings, you say this E factors actually is very strange or it's very special to the community of the physics. So nowadays, there are a lot of the method to derive these equations. They use the different method. For example, the Hills, this is Fujikawa's in the 1979, give a very elegant argument. He says that actually is the classical actions is not broken. So in this case, but the so-called quantum measures break the symmetry such that the partition function and so on. So you can get this equation. But I'm not the expert in the quantum field theories or elementary particle physics, but we know this equation actually have a lot of the applications in the quantum field theories and the elementary particle, the physics, very important equations. So for us is that it seems this is very hard to understand as theorists have a background of condensed matter, the physics. So we try to understand these equations from their as a series of the condensed matter, the physics. So we know that fortunately, so the Dirac particles in the electromagnetic field is actually can be solved exactly. So we know the charged particles in the magnetic field is equivalent to a simple harmonic oscillators, right? The problems. So for the Dirac Fermions, it can be also solved exactly. So now we can do this, suppose in the electromagnetic field. So we need to introduce this, this is A's vector potentials. So we have a freedom to choose a gauge in these problems. Here we simply choose this gauge. So such that the Px and the Pz are still good quantum numbers, right? But these are Hamiltonians is a functions of the, related to the y coordinate, so y, and independent of the x and z. So now we can introduce our annihilations and creation operators. So such that this is equal to the A and A DAC, the two operators. So we can write this, the P, now it becomes the pi dot sigmas. In terms of this creation and annihilation operators, and the Kz is a constant. Kx, is hidden in the expression of the A and A DAC. So that means that different, the Kx can give you the same result. This is related to so-called Landau degeneracies. So now it's very easy to find the eigenvalues. For example, if this is equal to Z and this is 8 zeros, kit zeros means this is the eigenstates for the A DAC A. That is from the simple harmonic oscillators, so we can get these ones. So in general, we can find the eigenstates and eigenvalues for these pi dot sigmas, right? This is just a 2 by 2, the matrix problems, so can be solved exactly. So except for this so-called the n, I said this is related to the eigenvalue and A DAC A. Is equal to the n, and n is integers. So we can diagonalize this the pi dot sigmas and find the eigenvalues and the eigenvectors. So we find that actually it's this pi dot sigmas that has the two eigenvalues. For each the n, it has two eigenvalues and eigenvalue. And a very special case is the so-called the n equal to zeros. If the n equal to zeros, we can find only the one eigenstate. But if the n is not equal to 0, we can find the two eigenstate. The eigenvalue, this k, the chi n's, it can be equal to the positive and the negative 1. If n is not equal to 0, and it is equal to this kz, is the eigenvectors for the PZ. Right? They should be changing signs according to the signs of the KZs. So if you use this as basis, the Dirac equations is should. Yes, you can hear me?
Okay. Okay.
Okay. Okay.
Yep.
So after you got all the eigenstate and the eigenvalues, you can use this as a basis. So all the operator can be expressed in terms of the eigenstates, this eigenstate. So now I show you this is the so-called the Landau levels for the massive Dirac the particles. So now the here we have a so-called the gap. This is related to the two v squares, and except the n equal to zeros, the here this is non-degenerated except for the Landau degeneracies. So these are eigenvalues for the so-called helicities. Helicity changes signs. This along this direction. This is the QZ. So for the other Landau levels, the n is not equal to zeros. It is always equal to positive and negative 1. It is a uniforms. So this is very special. The properties in these spectrums. At this 2 point, the helicity changes sign. So now, if you apply the electric field, so the problem becomes a little bit complicated. So we know that the electric potentials, we just consider a uniform electric field. So this potentials is simply equal to E dot the R. So E is electrical field, right? This we have 3 directions: the X, Y, Z, right? X, Y, and Z. X, Y, and Z. So if you calculate the commutators between the helicities and the Hamiltonians, now we have to introduce these additional electrical potentials. So we'll find H is a functions of the PZ, the momentums, and here the V electrical potentials contains these coordinates. So these 2 do not commute with each other. So in another word, so electric fields actually break their helical symmetries or helicity. So we find this is not equal to zeros. But for the chiralities, because this is independent of the matrix, I mean, or you say this is a matrix, is a identity matrix, the chirality is still conserved. It's still conserved. Now, we can use this eigenstate and eigenvalues, eigenstates as a basis, or the observer can be expressed in terms this the vectors, right? This is from the quantum mechanics. So now we can calculate these commutators. Finally, we can reach a very simple result. So now these commutators, because this is related to the helicities at the zeros Landau levels. The R positions are righted in the momentum space instead of the position space. Since this momentum, I mean, so the helicity changes signs in the along the KZ. So you will find these commutators is not equal to zeros. The change of sign at the KZ equal to zeros, right? We have a jump. So in this case, we find these commutators actually is not equal to zeros, especially if the QZ is equal to zeros. So what's the meaning of this QZ equal to 0? Actually is correspond this 2 point. 2 point. If you calculate expectation volumes for these commutators, so the here, this is a 1 over the IH bars of these ones. It comes from the, this is a partial the T of the H bars, right? It should be divided by these are IH bars. And here we have the summations of the QZ and the QX. So for the QX, actually this is degenerated, corresponding to the so-called Landau degeneracies. Landau degeneracies in the per unit is equal to the EB of the 2 pi H bars. And another one is one of the pi come from the QZs. So then you can get the simple the result. This is actually the E square of the 2 pi squares H bar squares times E dot B. And it depends on occupancies of these 2 states. So if this is a state, is an empty, it contributes to 0 to these expressions. If it is occupied, we got 1, right? So now it depends on the chemical potentials. If the chemical potentials at the valence band, it is equal to 0. It is equal to zeros, right? If this is the chemical potentials located between the band gap, right? It is equal to 1 because this state is occupied. And if the chemical potential located at the conduction band, so you see, is equal to 2. So now you got 0, 1, 2, 1, 2. But something wrong in scales, maybe you fail, because if the chemical potential is within the band gap, we find this equations is not equal to zeros. So that is if the system is fully filled, you get a non-zero the terms helicities. This is obviously is different from the physical intentions, right? So now we need to derive these equations very, very carefully. So to see what happens. So now we use the definitions, so introduced by the Jackiw and the Johnson's approach to derive this the chiralities equations. Now we apply this method to these helical problems. So in these problems, the current densities actually is introduced like this. So we need to, in the electromagnetic field, this is actually, we need to introduce a definition for the current. It should be invariant in after gauge transformations. So we know that we can introduce different gauge for the A and the phi, right? So if you introduce these ones, so units, so these are terms, so this is from the Z point to to another ones, epsilon should be very, very small. So usually if you take the epsilon approach to zeros, so you can get the result. But for free particles, the problems or in most the condensed matter problems, these terms has no the physicals, the E value. But here, because we have a so-called infinities, the Fermi Z, then we find we can have a so-called anomalous the correction terms. These anomalous correction terms also has the same forms of this E dot B, but have a minus signs. So after you introduce these terms, then you can get the result for the helicities equations. So that means if the chemical potentials locate within the band gap, so these terms, the 2 terms should be the cancelled exactly, or you say the anomalous the terms is cancels with these non-zeros, the helicity terms. So based on this result, then we got the first equations for the helicities. So the next, what's the equation for chiralities? But you say chiralities are a lot conserved, right? After we introduce the finite mass. So this is not conserved. We can get the similar equations if we use the same the gauge invariant definitions for the current. So we have two terms. The one term is anomalous the correction. Another one from this symmetry broken terms. So in the linear correspondence, the response to the series, we can find this so-called pseudo scalar densities. It is also related to the E dot B electric field. So finally, we got the equations for the chiralities. So find this is not equal to zeros. So you may say, oh, since the mass break the symmetries, of course, this is not equal to zeros. But these terms, it depends on the Kf over the mu. Mu is the chemical potential. So now, but what's a relation to the chiral anomalies, right? We are interested in the so-called the chiral anomalies. So if you take the mass approach to zeros, if the mass approach to zero, the chiral symmetry should be restored. So in this way, you find these terms approach to one, not approach to zeros. So if this is approach to one, actually we got the equations for the chiralities. So we can get the chiral anomalies equations when we take the mass approach to zero. So this is very special. We can see why we call this as an anomaly, because the symmetry breaking terms approach to zeros, but continuity equations is still break the symmetries. So these are typical the features for these anomalies. So now this is the result for the. So for the helicities, we find this is dashed red lines is for the helicities. It is equal to 1, -1, and 1, the 1 and the -1s, and equal to zeros in the gap. But for chirality, mass is not equal to zeros. It is not a constant. But this approach to 1, if you take the mass approach to zeros. So another problems, since we got the two equations, you may ask her, which one is the measurables, right? But we know that for the helicities, it has a very definitions. I mean, that is the spin projections at the direction of the momentums. This is the physical observables. But the chiralities, it's just the so-called the tau ones. What the tau one means actually has no the physical correspondence. Otherwise, or you can say this is not a physical observables, not physical observables. So what's our physical effect is for this helical symmetry breakings? I mean, this is related, we give a name that the so-called the helical magnetic effect is. So if the potentials, chemical potential for the particles with a different helicities, I mean, a lot of equals. So we can calculate the current for the free particles has no other interactions. So this current actually is proportional to the magnetic field. So actually we can calculate this the terms directly. So that means if these are two, the chemical potential for the positive helicity or negative helicities, we can get the non-zero current. So I mean, we can also derive these equations and use the phenomenological approach. So this means for if these are two, the chemical potential maybe not for the different helicities. So this is time rate for these helicities, partial rho and partial the T, should be satisfied these helicity equations. So this term means that the energy transfers in the unit times, right? So if you want to maintain these terms, it should be balanced by the so-called the energy. It goes to the energies. You change there because the energy difference between the two types of the particle are not equals. So this side, this is related to the whole Joule heatings. So J is a current related to these problems, and the E is electric field. From these equations, it's very easy to find this the formula for the electric current, which is proportional to the magnetic field. So after we got this result, we would like to apply to some the physical the effect which was extensively discussed in the topological materials. That is the so-called the magneto resistivities. So in the topological materials, we find a lot of the materials, the negative magnetic resistance was observed. People believe this may be related to the chiral anomalies, a lot of the works. So if you use these equations for helicities, we can also derive a formula for the magnetos conductivities. So if you like, you can use this so-called the linear response, the theory to calculate the conductivities. But here also we use a different method. We say use this phenomenologically. And if you say this is the equations for the helicities, if you introduce some the scattering mechanism, so this equation should be the balance, right, in the equilibriums. So we can introduce this the tau h, these are scattering times. So in the equilibriums, partial rho, partial t should be equal to zeros. So we can calculate a difference between the particles with a different helicities. So then this is related to the chemical potentials, I mean helicity dependent chemical potentials. So then you can substitute these equations for the electric current. Then you can get the expressions for the current, which is related to this the scattering mechanism. So finally, we can get these conductivities, which is proportional to B squares quadratic. So then you transfer to the resistivities, then you can get the elective the magneto resistivities. So now there is a question how to calculate the scattering the times, right? Different the scattering mechanisms can give you different scattering times. For helicities, so if you consider two different impurities as scatterings, we can calculate these use the Born approximations. We can calculate this tau. So in this way, we can get the elective the so-called magneto resistivities. So interesting, sir. The problem is that if we can find a very simple the systems, which has a very similar the effect. We call this Pauli Hamiltonians. The Pauli Hamiltonians is a result of the Dirac equations in the non-relativistic the limit, right? This is from the textbook quantum mechanics. The H equal to the pi dot sigmas, not equal to P of the two M's. So in this system, you find helicity is also, I mean, if without the electromagnetic, without the electric field, this helicity is also conserved, right? So we can get the similar equations. So in these equations, it has nothing to do with the so-called the chiral anomalies. So in the, about the not long ago, people, the Nielsen-Ninomiya say, oh, we can find this negative, the magnetoresistivity, which is related to the chiral anomaly. He used a very famous, this Landau level, the pictures. So you can see, if you start from the point of view of helicities, you'll find these pictures actually is related to the helicities, not related to the chiralities. So you can see this is actually has nothing to do with the chiral anomalies. It should be related to the helical symmetry breakings. So we can also apply this result to some other physical systems. So these systems is extensively discussed in recent years, and it observed the negative magnetoresistance. And most important, these systems actually has a energy gap. So that means chirality is not conserved, but we still observe the negative magnetoresistance. So in this work, they use the string method technique can controls the gap of the band gap of the systems. So now he measured this negative the magnetoresistivity and give a result to find this conductivity is proportional to the B squares, and you can tune the mass and give you a different result. So we use our theory to fit experimental data. The final result looks very perfect. So anyway, what's my summary is of this talk? The first, we got the two equations for the helicities and the chiralities. And in the massless limit, we rederive or reproduce the equation of the chiral anomalies. And from this point of view of the helicity, it seems that the chiral anomaly is just the accompanying effects of the helical symmetry breakings. So helical symmetry breakings is more fundamentals than this so-called the chiral anomalies. So this is what we want to talk today. Thank you very much.
Thank you. Thank you for the very nice talk. So I'm so surprised the chiral anomaly should be corrected by helical anomaly from now. So, is there any question from audience? So Professor Shen, actually I have a question then. So you said in massive Dirac Fermion case,
yes,
whose system shows the helical symmetry?
Yeah.
Right. So when you apply magnetic field, then helical symmetry is broken. Then,
if it's subjected to a magnetic field, the symmetry is still conserved. But if you introduce an electric field, the symmetry is broken.
I see. Then if the helical symmetry is broken, but you say chiral symmetry still survives.
In the massless case, for massive case, the chiral symmetry is also broken.
Also broken, I see.
Yeah.
Okay, but in massless case, then we can still say chiral anomaly still exists, right? In your case, it's massless case, right? Yeah.
And that means this two equation can be applied to the two cases. So if you take the mass approach to zeros, we can reproduce the so-called equation for the chiral anomaly.
But for example, in Dirac materials, when we there's a helical symmetry exists in Dirac materials. So when we apply the magnetic field, then helical symmetry is broken. Then chiral symmetry survives. In that case, you have kinds of two modes, something like that. So you can choose upper part or about lower part, depending on the magnetic field directions.
Okay, I mean that's
That's the Chiral anomaly. What I understand, but
it's a very good question. So
yeah.
if the chirality and the helicity, both chirality and helicity are physical observables, this looks impossible. But here, for my understanding, helicity is a physical observable, but chirality is not. So this maybe is that give you these impressions. So chirality, I mean, chiral anomaly itself, actually, I mean, chirality itself is not physical observable. But the symmetry is respect when they introduce the magnetic field and the electric field.
Okay, yeah, let me think about it and let me link your paper. Then I will question again later. Yeah. So we have a few minutes. So is there any question from the online audience?
It looks like Professor Taegon Kim has a question.
Oh, I see. Yeah. Please go ahead.
Okay.
Yep. So thanks for the nice talk. This is Taegon from KAIST. So I have one simple question. So you showed that this helicity is given by the sign of KZ.
Yes.
In the valence and the conduction band. So can you tell us more about what happens exactly at 0 kz?
0 kz. That's the point. I mean, just that the state at the top.
Yeah. What's the state
of the valence band and the buttons of the conduction band, the states. So when this is a Z. I mean, this is a QZ, right, along these directions. And on this side is positive, on this side is negative. It is continuous at this point. I mean, only for the states. Yeah, n equal to 0. We have 2 bands. But for the other bands, this is always the positive one or negative ones. So it is continuous in from the negative the QZ to positive QZs. So we don't need to consider contributions from all this state. Only focus on the 0 energy, the n equal to 0 states. So because this obviously is a QZ dependent, so it do not commute with the electric field because the electric field is a potentials, the V along the Z directions. So it's related to the proportional to the coordinate, the Z. So this Z in the momentum, the space is a partial KZ, right? The momentum space. The partial KZs do not commute with these chi zeros. So that's why this is not equal to 0.
All right, thank you.
Okay, since time's up, let's just thank the speaker again. Thank you, Professor Shen. And
Okay, thank you.